Hi, my name is Untitled, and today we want to use some theory that we've talked about already. This is about boundary conditions, and now we want to apply it to 2D shells. Those are circular 2D shells. So in real life, it basically looks like a disk with a very small thickness. Okay, and the loading is in the plane of the disk. Okay, the loading could be some, I'm gonna say some tensile stress here. Okay, in the plane of the disk. So now what I'm drawing here is like the top view. Let's say W. How does it look like? It's something like this. And what we want is to figure out what are the stresses, the normal stresses in the radial direction. So basically, if we define a center here for this disk, what are the stresses in the radial direction are, and the stresses perpendicular to this radial direction, that would be a direction phi. I can't really draw it here, but it will be 90 degree to the r direction. So if we draw like an infinitesimal element of this disk, let's say some element that's here, I'm gonna try to draw it in 3D kind of. This is the thickness, maybe chi or something. This side will be in the radial direction, something like dr, and this one would be in the circumferential direction, and something like d phi, the circumferential direction. So something like this, and this part here will be like the d phi here, or we can take this one. This is this will be, this side will be a little bit bigger than the previous one because we moved already in the radial direction. This will be like a d phi plus a specific change. It's not really important here, but a d phi plus a change caused by the, because we moved in the r direction. So something like a d phi divided by dr, I'm sorry, partial derivation, dr, yeah. And here we can say that the gr part here on the left and on the right are equal. It's okay. And what I want you to draw here, the reason why I did all this was to show the stress in the radial direction would be this one, is the stress in the direction of r, in the direction of the radius. I'm just drawing it here with one arrow, not with like a surface load. I hope it's fine. And the circumferential stress is like perpendicular to it, in the direction perpendicular to it, it would be this one. So this would be our sigma phi. It's in the circumferential direction. So if sigma phi is on this side, for example, you see, yeah, and r is would be on, let's say this is the green side, this one would be there, okay, in the direction of the sigma r is in the direction of the radius, basically at any random point. So we could actually take another element there, and sigma phi is perpendicular to it. Anyway, we're not really here to go deep in the theory and stuff. We actually want you to see how to use the formulas that are known for these 2D shell. And we have the following formula. It's like the area stress function that's given with a plus b ln from r here is the radius, plus C times R squared. A, B, C, and G are basically constant that need to be determined. There's a last part here with G. Actually, we could cut it off already because G would need to be 0 for our stresses in the radial and circumferential direction to have finite values, but we can figure it out later together. So sigma the stress in the radial direction is given as 1 divided by A times the first derivative of F. By the way, with derivative here, we mean the derivative with respect to air. Okay, that's what we mean here with the derivative. So we can basically compute it. A will be 0. This term will be 0. B times derivative of ln r is 1 divided by r. So C times 2r, then that's the derivative of r squared with respect to r, plus, like I said, g needs to be 0, but I'm going to show here why g needs to be 0. So let's just do the derivation first. We're going to use the product rule. We can derive r squared first. It becomes 2r, and we let ln r be. And then we take r squared, we let r squared be, and we derive ln r. Ln r is derived is 1 divided by r. So we obtain b divided by r plus 2cr plus g times 2r ln r plus r. That's sigma r. By the way, here when we talk about two t-shirts, there's a possibility to use the stress like sigma. That would be the unit here would be something like Newton per millimeter squared, or we could also use a kind of line load. So if sigma is the force divided by the area, in this case here the area could be T times G phi zum Beispiel. I'm sorry. For example, that's an area. We could also do the following. We could multiply that sigma stress times the thickness, and what we would obtain would be something like a line load, a little bit like what I drew here. It would be not the stress over a surface. Let's say if we had to draw it properly, sigma r would be something like this on the disk along the if this is a disk, let's say on the surface of a disk all around. And now we want to simplify it and use maybe just a line load that we could draw. Oops. Like this. It's also a radial. It's going all over the circumferential length. So it's just a simplification for sigma r, and we could call this one nr. And that's a possibility. So nr would be sigma r times the thickness g. Okay, just another possible notation here. Yeah, so this will be sigma r. And you can see here that for r equal 0, for example, for r equals 0, or is it really a problem here? We're gonna discuss about that g right away, but let's do this one, sigma phi first. Sigma phi is f, the area stress function derived twice. So we have derived it here once already. Oh, by the way, I forgot something. I forgot the 1 divided by r. I'm gonna put it in the front. 1 divided by r. Okay, so if we do it here, it's gonna be b divided by r squared plus 2c. This r is gonna go away. And here, if we divide this time, by r, this r is gonna go away, and that one is gonna become 1. So sigma r is basically b divided by r squared plus 2c plus d times 2 ln r plus 1. I think here you can see already that if r is 0, for example, if we want to figure out what are the radial stresses here in the center of the 2G shell, because of the ln r here, we're going to have minus infinity, meaning that the stress will be infinite. Okay, and we want to have finite stresses, so this constant here need to be 0. We don't want such a term because it's going to lead us to infinite value of some stresses. And so we need here G to be 0. G must be 0 so that the stress would remain finite. And we're going to see the same thing here with sigma phi. Sigma phi is F derived twice, double differentiation of f. Where's f again? There's f here. We've differentiated once already, so we can just differentiate this part, this one again. 1 divided by r is just gonna be minus 1 divided by r squared. 2cr divided by r is gonna be plus 2c. So 2c, 2c, yeah. And here, what are we gonna have? Sorry, here, so plus d times, I'm gonna put the 2 outside of the bracket, and r, ln r needs to be derived. We can let r be and derive ln r. It's gonna be 1 divided by r, and then we can derive r is 1 and derive ln r. I'm sorry, we can derive r is 1 and let ln r be. Yeah, ln r just remains there as it was. And yeah, that was for the first part. And then this is just r. R squared divided by r is r, and r divided by r differentiate with respect to r is 1. So yep, we're done. You can just write it in a more presentable way. Plus 2c plus g times, this is r divided by r. This is basically 1. Okay, in here that's basically 1. So we have here 1 plus ln r times 2. So it's 2 plus 2 ln r plus 1. So it's like 2 ln r plus 3. And again, you can see here that the circumferential stresses for r equals 0, for example. So when we want to figure out what are the circumferential stresses there at the centrum of the center of the plate, of the 2D shell, we're gonna have problems. In this case, we're basically also gonna have problems with b, but I want to talk about g first because this is a value that needs to be 0. Like, we basically need to take it out from our whole equations here. So ln r is gonna be minus infinity, so this section here is gonna be infinite. So we don't want this, therefore d needs to be 0 for the same reason as above. This d here needs to be 0. Okay, yeah, what else? We can also see that the problem, what we're talking about here with for G, we basically have the same problem with the value of B. When r is going to be equal to 0, then at the center of the 2D shell, this term here is also going to go to plus infinity, as well as the whole one with the minus sign is going to go to minus infinity. So in this case, b also needs to be 0, so that sigma r or sigma phi, doesn't matter which one, and at this point can be, so that they can be finite, so that they remain finite. Okay, so b is equal to 0. That's one constant that we basically have already. G needs to be eliminated from the whole equations, as I said, and we still need to figure out what C is. So how are we gonna figure out what C is? We're gonna use the boundary condition of the load. So basically, we know what is the loading at the position, which position r equals to, we can define this radius, don't know, let's call it o, like our radius. So at the position at position r equals to outer radius, sigma in the radial direction is known, and it should be equal to this value here. We can call it P like pressure, and small r like in radial direction should be equal to PR. Let's just call it PR. Okay. How can we use this condition, this boundary condition? We have the equation. What is our equation? Sigma from r equals r outer radius is, you can read it here, b divided by r squared, but b is 0, so we can just let it out, is equals to 2c. Then the g part is also 0, we said it already, so 2c needs to be equal to PR, and then we can figure out that c is PR divided by 2. Okay, there's something else that's very important to know here. The stresses, they are positive when we have like stretching, basically. So when we have elongation of the element, or when the element is under tension, and they are negative when we have compression. So basically, the stress that we have here are kind of like elongating the disk in the radial direction. Those are like tensor stresses in some sense, at the boundary at least. Okay, what happens inside can be calculated with our formulas, and it basically remains, you see here, with the value of c, we can figure out what sigma r actually is for any random position of r, because you can see in this case there's no function of the radius anymore, so the stress in the radial direction is basically gonna be constant. It's gonna be 2 times c, so it's basically gonna be equals to PR, constant with the value PR. And the stress in the circumferential direction, what is it gonna be? The stress in the circumferential direction, in this case, it's also 2c, because B0, D0 is also 2c. Both are equal in this case. There we have our stresses. We can go further and investigate the deformations of this disk. So what can we do to come that far to get those information? We can investigate, we can use the formulas of strain in radial direction and strain in circumferential direction. Those are the same formulas that we use in engineering mechanics. So 1 divided by the Young's modulus of sigma in the radial direction minus Poisson's ratio times sigma in the phi direction. And here, sigma in the phi direction minus Poisson's ratio times sigma in the radial direction. And this is like a two-dimensional stress. It's like a plane stress state. Yeah, and in our case, in this case, sigma r equals sigma phi. Okay, here sigma r equals sigma phi. So that means that epsilon r is also equal to epsilon phi. So basically, we're saying that if you have sigma phi here, it doesn't matter, sigma phi and sigma r are basically the same. So both formulas would be the same in this case. Okay, in this case. And yeah, so, and what is it? We can just put in the formulas that we just had, the values for sigma r and sigma phi. So epsilon r equals epsilon phi equals 1 divided by E times sigma r was it? PR minus mu times PR again. So this is 1 minus mu divided by Young's modulus times PR. Those are the strains. Okay. And what is the strain? The strain is a ratio of the deformation that occurs divided by the original length. That's like a simplified definition of the strain. So if we actually want to figure out which deformations happen in the radial direction, for example, we would just take ER as so. Let me repeat. So epsilon r is basically UR divided by the whole length in the radial direction. Actually, I don't know if it's better to write it that way. It might be better to write it as a differential. Okay, I mean, let's just, we could actually do it, but let's just control the formulas with the results we've gotten here. So this one and the stresses and stuff. Let's have a look. Let's see if they are correct. So you can check them in here. The book is called Static Deflection Hackwerk. You can from Hack. Oops, no, that's just like printed version. Where Erwin Hake and Konstantin Mescuri, so you can check it. But it's in German, so. But apart from that, in English, there's also a very nice book about placing shares from Ray Clow, I think. It's just called, I think it's really just called Plates and Shares. Wait. Yeah, I think it's just called Plates and Shares. Wait. Or I think maybe it's called Theory of Plates and Shares. I'm not really sure. Finally, I'll need to check it. What are the formulas I'm looking for? Here they are. Lucky. So we want to see what is NR. Okay, as you can see here. Okay, the book is using that all the stress, like that line stress kind of, okay. And they basically say that NR, so NR is like sigma times T. So they say that sigma times T is gonna be and that stress they call it R, but it's also a line stress here. So they say sigma R stress in the radial direction times the thickness is gonna be R, the actual the external stress, the loading in the on the boundary, times R2. So basically both of them are equal, and the same goes for the stresses in the circumferential direction. So that's basically correct. That's also what we got here, that our stresses are basically the same as the external loading there. And what about our delta R here? Now that this is the deformation in the weather direction, what did we figure out? We figure out that the strain in the radial direction equals the strain in the phi direction, okay, equals 1 minus Poisson's ratio um, divided by Young's modulus times the stress, that's the strain, okay? And as I also say, the strain is basically a ratio of the deformation that occurs in this direction. For example, R here in the radial direction divided by the original length. So if we want to have the actual displacement in the radial direction, we're just going to multiply this ratio, this strain times the original length, okay? So you see the Imes, sorry, 1 minus mu, what they call mu here is the same that I called nu here. Some books call it mu, others call it nu, but it's the Poisson's ratio. So 1 minus Poisson's ratio divided by E, okay. They also have something here divided by H. Okay, why is that? We're gonna see what they call H here. It might be the thickness. Times A. Wait. What is that? Okay, at the position A. So if we are at the position, for example, the wall displacement in the radial direction, what will it be? It will be the strain times the original length, so basically the wall radius of the disk, and that's A in this case. So U or delta, how do they call it? Delta R would be epsilon R times A. Times the radius, we call it here in our case, we call it R O, like the outer radius. And it would be, let me close the book first. It would be, if we just want to write it in the same manner as it was in the book, 1 minus mu, and here E, Young's modulus, our stress PR times the wages is itself RO, okay. And then in the book they have something else. They have an H here. And why do they have an H here? The reason is, it's simple. We have sigma. We are using where was it? For our stress PR here, we are using sigma equals PR. That's what we say, right? But we also said the following, that NR equals sigma R times the thickness. Okay, I call the thickness T here, small t, but they call the thickness H. So they're basically saying that NR is sigma R times H. Okay, and now in our formula here, we've used sigma already. We were using, where was it? We were using sigma over here. Okay, so you have a strain. Wait, am I missing something here? PR. Yeah, exactly. So that's what we have, right? And we figure out the following: sigma R equals PR. If we put it in here, we're gonna have NR equals PR times H. Okay, so PR, the value we have here in our formula, PR is gonna be NR divided by H. I mean, I wonder if this is like the right way to express it. But what I mean is that the line, maybe I didn't really need this. The What we have here for us, PR here is already a stress in the term of Newton divided by millimeter square. And that's basically how I should explain this. This is already a stress in the term of Newton divided by millimeter squared. But the stress they have in this book here, they're working with line stresses, basically. I'm over here. They're working with line stresses. So the unit the stress have has over there is Newton per millimeter. But in this formula here, we actually need the actual stress with the unit Newton divided by millimeter square. Because if we need to have a strain here, then the the Young's modulus has the unit Newton per millimeter squared, for example, and on the numerator, we need to have the same unit, Newton per millimeter square, not Newton per millimeter. And that's why they need to divide their value, their R value, that's actually Newton per millimeter. They need to divide it by the thickness in millimeter, for example, so that they get the right unit, Newton per millimeter square, for the formula. So this is basically correct, what we've done here. And yeah, so next time we're gonna look at the other cases. We're gonna look at Chuji shares with some gap in the middle and the loading here on the outer boundary, and then we're gonna look at the same case with the loading on the inner boundary, and we're still gonna use those boundary conditions and the same equations we've written here to solve those cases. So thanks for your attention, and see you next time.